let us talk about the seismic and electrical methods. Seismic refraction methods. It is one of the geophysical surveys that is most commonly conducted by engineers during investigation. It produces the most basic of the geologic data by geologists or engineers through plain procedures with equipment. Refraction, shock waves are deformed or refracted due entering a material of various elasticity, like the way that light waves are deformed when passing through the water-form air. Reflection, shock waves are bouncing from surfaces of various media, like the way that the light is reflected from the mirror. Theory. The propagation of waves in elastic medium is the basis of seismic investigation. Homogeneous, isotropic, elastic media are considered as soil and rocks in the theoretical circumstances. Any deviation from the isotropic condition and assumed homogeneous can be expounded to show changes in depth and nature of subsurface of the geologic units. Seismic waves. It is any mechanical vibration that is commenced by a source and moves towards where the vibration is noted. The vibration emerges in all directions, the displacement is supported, and due disturbance, it is merely a change in the stress state. The vibration readily passes to one another from a medium, from solids to liquids, or gases and vice versa. There are two major classes of seismic waves, the body waves and the surface waves. Body waves. Body waves pass through the volume of a material or all media that carry noise in gases, including the atmosphere or air waves. These are called pressure or compressional or primary wave, P wave, which are the fastest traveling of all the seismic waves. Secondary, transverse or shear wave or S wave moves slightly slower than P waves in solid. P waves can only travel to materials that has shear strength, therefore, it do not exist in liquids and gases, as no shear strength is presented in the medias. S waves may be provided by a source of traction or by conversion of P waves at the boundaries. Surface waves. Surface waves move slower than body waves, thus these waves reduce rapidly with distance from the surface. It is produced by explosions, surface impacts, and waveform transformation at the boundaries. It exists only at surfaces or interfaces that is the two perceived vibrations, the Love and the Rayleigh waves. These surface waves may have more energy composition than body waves wherein it may cause more damage from the vibrations of an earthquake. Collecting of data. The production of better seismic equipment has been perennial to allow because of data electronics, wherein newer equipment is hardier, more efficient, and able to store more amounts of data. Sophistication of survey partially manages the choice of equipment and the field crew size necessary to acquire the measurements as the survey that is being initiated will be the basis of the choice of equipment and source of seismic waves. Sources. The source of the seismic waves may be a hammer smacking the ground or an aluminum plate or weighted plank, shot from a rifle, harmonic oscillator, or explosives. A geophysical contractor should be given a guide if the source of the task will be changed or selected, as he or she should be vigilant not to go beyond the requirements, permits, and other agreements. The portable seismic instrument, geophones. It is the sensor that receives the seismic energy. These sensors are either velocity transducers or accelerometers that transform ground movement into voltage. The profound value of particle cannot be determined unless geophones are regulated. Seismographs. It is the recorder of the inputs of geophone voltages in a sequence of time. An elaborate amalgam of equipment that sense or trigger the source, geophone signals, and other data is the seismograph system. However, in engineering and environmental surveys, Sophisticated seismograph equipment is not normally mandatory. Amplifier recorder. It is essential in electronic amplifying and timing device. It amplifies the times of the interval between shock and current generation of the geophone due to the arrival of seismic waves and the minute electrical current received by it. Having a frequency of 1000 cycles per second by an electrically driven turning fork, which is the most time that the device recorded. In seismic surveying, good operating techniques and correlation are essential if adequate field data are to be collected or interpretation. Geophone layout. Reverse seismic profiles are essential to acquire a factual picture of conditions of the subsurface. Subsurface interfaces which are not parallel to the ground surface will construct apparent velocity and subsequent velocities which are greater or less than the material's true velocity. Energy sources. Mechanical or explosive are used in seismic survey. Mechanical energy sources slam directly upon the ground surface. Using include 8 to 10 pound sledgehammers striking a plate or tamper devices. While explosive energy sources can be used to exquisite advantage where signal mitigation and noise levels require more energy than mechanical energy can provide. Geophone locations. The numbered positions can either be geophone locations or multiple channel system or hammer positions for single channel systems. The different layouts gives more or less definition near the required surface. Regards that there are changes of the end positions for forward and reverse spreads, and the number and spacing of positions can be modified as required. Electrical resistivity method. Electric geophysical prospecting methods locate the surface effects provided by the flow of current in the ground. Basically, the massive variation in electrical resistivity found in different rocks and minerals. The principle of utilizing electric current to the earth between two electrodes and two or more electrodes, measuring the latent difference between it, and it is where the electrical resistivity depends. The data that are used to make subsurface conditions and interpretations is the distance between the electrodes and the measured latent difference. Theory. Different materials are different in terms of their ability to conduct electricity. In some minerals, at least one atom is loosely held, but it requires only external influence to convey some electrons from atom to atom of the material. While in other minerals, there are few free electrons and they poorly conduct electricity. Both types of electric conductivity are involved in the electrical resistivity. Electronic conductivity through the rocks and soil particles, and electrolytic conducting in the groundwater. The higher the conductivity is when the more groundwater are mineralized. Electrical properties of rocks. All materials, including rock and soil, have a fundamental property: resistivity that controls the relation between the gradient of electrical potential and the current density. The electric current conduction takes place virtually through the whole water occupying joint openings or pore spaces, since most rock and soil forming materials are basically non-conducting. Metallic sulfides such as distinctly magnetite, specular hematite, pyrite, carbon may be found in adequate concentration to grant measurably to the conductivity of rock and soil. Classification of electrical methods. Since the first application around 1830, the number of electrical methods used is truly large, including the self-potential or ST, telluric currents, and magneto-telluric resistivity, electromagnetic or EM, and induced polarization or IP. One of the common methods is natural or artificial, that is involved by type of energy source. Another classification, the data are measured in frequency or time domain by grouping. Time domain methods are those in which the magnitude and shape of the received signal is measured, while the frequency domain source methods and measurements are made during active source. Portable resistivity equipment. The portable resistivity instrument is formed of two components, a current source and either a bridge-type circuit for measuring conductance or resistance, or separate circuits to measure the potential and current separately. R50 stratometer for deep electrical resistivity surveys. Earth resistivity meter, model ER2, uses 4 or 5 electrodes which measure electrical resistivity of soils, rocks, and minerals, etc. R40 Stratoscout resistivity meter, used for electrodes which measure directly in ohm resistance, and this instrument has built-in calibration circuit. Resistivity unit, set complete with measuring instrument and commutator, dry cell, battery power supply unit, 2000 feet of cable, 4 reels, 5 electrodes connecting cables, where it reads from 0.01 to 1000 ohms. Operation techniques. As with seismic surveying, if adequate field data are to be collected for exposition in electrical surveying, great operation techniques are essential. Electrode configuration. There are numerous configurations or arrangements for placing the current and potential electrodes for surveying. There are 3 most appropriate for SCS geologic investigations: the Wiener, Lee, and Schlumberger configurations. Wiener configuration. This configuration uses 4 electrodes partially spaced along a line. The outer electrodes serve as the current electrodes, and potential electrodes are the inner ones. Lee configuration. The resistivity meters are built to be used only for a 4 electrode array, but it can be converted into 5 electrode configuration by utilizing a 5th electrode. This configuration is a splitting method where the assumed resistivities from P1 to P0, P0 to P2 are being measured. Schlumberger configuration. The fundamental advantage in this technique is that the local inhomogeneity's influence is close to the potential electrodes and can be clearly sighted on the apparent resistivity curves. On the other hand, the local heterogeneities do not appreciably modify the shape of those resistivity arcs of curves, which have been came up with a given Mn, rather they only supplant the arcs as full units.